Hi, everyone. Thank you. We're doing a co-presentation here, and the title of our talk is a feasibility assessment of algal biomass removal from Upper Klamath Lake. By algal, we actually mean cyanobacteria, but we'll get into that in a little bit. We had two funders on this project. National Fish and Wildlife Foundation was the fiscal agent, and US Fish and Wildlife Service funded the majority of the work. Our project team was actually rather large. This was a pretty complicated project, certainly much more complicated as we got into it, compared to what we thought when we started the project. Stillwater was in the lead, but we had really important contributions from SFEI. Randy's going to cover some of that. Also, Jay Kahn at Aquatic Ecosystem Sciences. We had Eli Asarian of Riverbend Sciences. We also worked with OIT. Professor Erin Cox, who's not with OIT anymore, but she worked with us on the project, and a couple of her students were actually really critical for some of our pilot studies. And we had a steering committee throughout this project that helped us be a sounding board for technical work on the project, helped keep us focused on the objectives that included National Fish and Wildlife Foundation, US Fish and Wildlife Service, the Klamath Tribes, Oregon Department of Environmental Quality, and the California North Coast Regional Board. Okay, right then, thank you. All right, so the project purpose is here on this slide. What we're trying to do is assess the feasibility of harvesting Aphanesalmonon plus aquae, or AFA, so that is actually cyanobacteria species, from Upper Klamath Lake as a potential near term, and when I say near term, we mean roughly within the next 5 years. The idea is to improve water quality for lost river sucker and shortnose sucker, the federally endangered fish species. And the near term is really important. There's an existing harvest industry, which Randy's going to tell you a little bit about in a minute. And so the idea was, can we take advantage of this existing industry, scale up in a relatively short amount of time, and essentially harvest our way out of some water quality problems for the fish? So we wanted to think about how could we do this quickly, if at all. All right, so the first thing we did is look at current conditions in the lake, and I can't go into details here, but there's been lots of great work on water quality effects due to large cyanobacteria blooms in the lake. So I'm going to give just high level. We know that there are large seasonal cyanobacteria blooms. They tend to be dominated by AFA throughout the May to November period, although there's a few shoulder months in there. Really, the peak bloom is mid-June to mid-July. In most years, there's a little bit of wiggle room there depending on the year. The bloom decline occurs in mid-July to August. And we were basically looking at data from USGS, the Klamath Tribes. There's tons of monitoring work that's been done in the Upper Klamath Lake. There's been tons of analysis done by USGS. Jay Kahn has done a fair amount of this. Sarah Eldridge has put out reports. So we were really relying on other folks' understanding and science around. There's a raised hand. Hang on 1 second.
Excuse me, I'm sorry to interrupt, but we can't, everyone on Zoom can only still see Liam's slide, presentation rather. And so we're missing your presentation.
We don't want that. We don't want you to miss this. We're going to get that solved. Thank you for letting us know.
Great. Talk of technical difficulties. So going back to our blooms, there's been lots of great work done on this by numerous folks in the basin. And so we're taking that information and using it to describe current conditions and then think about how could we harvest the cyanobacteria that's characterized by those current conditions. I mentioned we have a peak bloom mid-June to mid-July. That's important because we need to know when should the harvest occur, should it focus. And then a bloom decline in mid-July to August when we see most of the water quality effects. So we'll look at those in a little bit. We also know that there's substantial daily and seasonal variability in the biomass. And what I'm showing you here with this set of tiles is actually, this is a remote sensing tool that USFWS has developed to look at cyanobacteria in Upper Klamath Lake and many other lakes. Here we're seeing mostly surface signals, although there is some penetration of that data into the water column. But what we're seeing in this top tile here, this is early June. So the color intensity here, the cooler colors mean there's lower abundance. Black means we're actually not getting a return signal on cyanobacteria. If we move to mid-July, when we expect that we'll have a peak bloom, we see that there's now reds and oranges. And the dark red means the highest abundance. Mid-August, we're starting to see bloom declines. We've got some yellows in here. And then October, we have certainly more effects of bloom decline. If I zoom in a little bit, it's kind of hazy, but what I want to point out here is important from a harvest perspective. Here's kind of our peak bloom, and this data was 2020 when we were actually out there in boats doing some pilot study work and data collection. You can see that these really intense red areas tend to be around the deep trench area east of Eagle Ridge, near Bear Island, Shoalwater, Howard Bay. That's important when we're thinking about where harvest might be most beneficial. If we then look at October 20th, now we're in certainly a bloom decline period, but we still have areas of intense abundance in these areas. So that's important, and we'll think about that a little bit more when we talk about harvest. Okay, so again, we need to link blooms and bloom declines in the lake to water quality for fish. We looked at effects on dissolved oxygen, pH, and unionized ammonia. I'm just showing you a little bit of data here from one of the USGS stations in the lake. This is the MDT station. It's in the deep trench just to the east of Eagle Ridge. We did wind speed analyses. I couldn't put those on the slide, so I'm just showing you very quickly water temp in degrees C 10 to 30, dissolved oxygen in the second tile down here, 0 to 20 milligram per liter. We also have phycocyanin data just in the surface waters. This is a log scale going from 0.1 to 100, and then we have pH 7 to 10.5. And the way these plots work is the daylight hours are shaded with this yellow color, the gray is nighttime. And what we see, we're looking at a little time transect here of August, 5 days in August in 2017. So this is just a kind of representative set of conditions for an intense bloom that's starting to decline, and we're seeing effects in water quality. So if we focus for a minute on phycocyanin, that's our cyanobacteria pigment. We're seeing much higher concentrations here in the initial part of this week, and they're starting to decrease. Again, this is a log scale as we move through the week. What are we seeing with dissolved oxygen? Well, the blue line is surface waters, red line is bottom waters, and we have supersaturated conditions during the day up above 15 milligrams per liter. If we go into the bottom waters, we're below 5 in many cases. We see that start to kind of step down, and we don't see those supersaturated conditions anymore as the bloom declines. We actually see the surface waters coming down to pretty low DOs, 5 and below, and they're similar to what's in the bottom waters. I will point out just quickly that there are periods of brief mixing that we saw in some of the data sets, indicating, when we've got DO kind of matching surface water, bottom water concentration. So we were looking at some of that data as well. pH, very similarly, we have, levels above 10 in the surface waters when these intense blooms are going on. Bottom waters are lower, but this is still pretty high. These are, chronic conditions for fish. So we're looking at all of this data and trying to link what's going on with algae and what's going on with water quality. Now, the next step was to understand what's happening with algal harvest. And so Randy's going to take you through a few of the slides there, characterizing how harvest occurs under current conditions.
Thanks, Maya. So for folks who aren't aware of harvesting algae in Upper Klamath Lake, there's been an industry for decades now that harvests the AFA. There are a lot of challenges to that because of the temporal nature of the conditions that the harvesters need to harvest the pure blooms of AFA. So they're always out during the bloom months. They're out scouting, looking for where the bloom is. It's chasing the algae, I think is the phrase they use. Because it has to be just right for them to be able to have the right harvest conditions. So, the key is to find a dense bloom. And if anyone's been on Upper Klamath Lake and seen a dense bloom, it's a thick scum. That's what they're looking for. And they're looking, they'll look closely at it to make sure it's these AFA flakes, and ideally not a mixed bloom with, with microcystis or gloiotrichia or other species present. That way it's a pure, they're harvesting, as pure as they can get. After that, what they'll do is they will harvest as much as they can while they can, because these moments in time where the bloom is just right, it can be fleeting. So there's a variety of techniques they can choose to use for harvesting. The key is getting out, like I said, as much as they can, and then removing as much of the water as possible. The slurries in the buckets in the lower right-hand picture, it's a thick slurry kind of standing up above the water there, but it's still only about 1 to 4% solids. The rest is water. So, the vast majority of what is harvested is still water, and that's expensive to transport, it's expensive to process, the more water you have. So, that's really critical to take care of that from the harvesting techniques perspective. There are a few different methods that they've used over the years. Method C is basically just putting a big pipe in the water and sucking the bloom out and spreading it over some screens to help try to dewater it. Method B is actually putting screens in the water, like a rotating screen kind of conveyor belt that will pull the algae out of the water, and anything else that's in there. And then there's a newer method that is much more specific to just getting AFA, that uses kind of a conveyor belt style approach, but with fishing line. And because we showed you the picture of AFA in the previous slide up here, they look like little flakes of grass, miniaturized, of course. But when they are coming to account with these rotating strings, they'll kind of wrap around the string and grab on, whereas microcystis or another algae or cyanobacteria species just doesn't get caught. So it's much more specific. So from getting a quality product, rotating strings really avoids some of the other species. But like something like method B with direct screening, you can get a lot more volume. So depending on the conditions of the bloom, they might incorporate method A or B from a preference perspective to get as much as they can while they can if the conditions are just right. In general, the biggest end use has been for dietary supplements, nutraceuticals. There are a lot out there on the market, super blue-green algae, that type of thing. Most of it on the market, if it's that super blue-green algae, it's coming from Upper Klamath Lake. There are other things that are other algae species like chlorella. Those are, not necessarily wild harvested typically. They're going to be, grown in facilities where they're cultivating it. So this is fairly unique in Upper Klamath Lake. There is some research out there to try to find other end uses for the AFA and algae in general. Biopharmaceuticals, things that might have, anti-cancer, anti-inflammatory properties. So, there's some, chemistry and research going on right now to see what is possible, because this is a mature harvest industry. So can they use that to produce something else? Also looking at, soil amendments and fertilizers. These, algae cells, they have phosphorus in them, they have nitrogen in them, a lot of, trace elements, things that can make really good, fertilizers and amendments. And so there's, some definitely opportunity there, as well as, cattle feed supplements. Again, this is a nutrient-rich food. So trying to find other end uses is something that I think is important for them. For the project that we're talking about, though, in terms of improving water quality, that concept doesn't have to be as selective as what these harvesters are currently doing, because it's not, going to be, something that's necessarily ingested by people directly. It doesn't have the same, kind of needs to be specific. So when we talk a little bit later, it's going to be about, how much can be harvested as fast as possible kind of a thing, just in order to remove the algae cells and its associated nutrients and, take that out of the picture for, the water quality impacts it has. In terms of the information on the right here, this is some of the things that the harvesters do in order to, ensure, a quality product. So there's a lot involved from their side for, before it gets in the bottle on the store shelf. And so just things to kind of consider, and that may not necessarily be something that if this were to ever occur for a water quality perspective, those things wouldn't necessarily have to happen. So Maia talked a little bit about the locations where we were seeing algae based on that satellite imagery. And often they're associated where the blooms are the densest is areas that are kind of protected from the wind. So, we'll call that kind of a low fetch area. So in general, there's a clockwise circulation pattern that's generally dominant in Upper Klamath Lake. Winds coming out of the northwest, create that pattern. And so in the study, we looked at a few different scenarios of how much area could be harvestable based on certain wind conditions. So in in our pilot study, we were looking at just here off on the trench, other areas like Howard's Bay, as well as areas here in the northwest. Those are also potential areas in that low fetch area. Once there is a lot more wind, the blooms just get broken up a little bit more. And so it's not quite ideal for the harvesters. The other scenarios besides the low fetch harvest areas is medium fetch, which again is just slightly windier. And then as well as another scenario that's kind of all fetch, basically the whole lake. What are those, how can we, figure out the calculations for what's harvestable looking at that? So anything else on the industry covered?
I think that we'll talk a little bit more about it when we get into kind of our expanded harvest scenarios.
Thank you, Randy. So the next step after learning a bit about how the harvest is happening under current conditions and what their current technology is, we then needed to make some estimates of chlorophyll in the lake and algae that they could take out with these sort of harvest scenarios. So the way that we did that is we estimated the algae in the lake using measured chlorophyll. I mentioned the Klamath tribes have been taking quite a bit of data for a number of decades, so we used that information. We estimated the phosphorus associated with the algae in the lake using an empirical relationship between measured chlorophyll, which was roughly on a 2-week basis, and algal total particulate phosphorus at Link River Dam. And we did that. KHSA has a data set there where they've done some more detailed analysis of phosphorus at that location. And actually Jake did the analysis here, and I'm showing one figure. It's actually a fairly complicated set of assumptions and calculations, but just to give you a sense that what we were trying to do here was relate chlorophyll at KHSA Link Dam location in microgram per liter to the total algal phosphorus, because this is what we think we would be removing when we're harvesting out of the lake, is the phosphorus in algae. And we're looking at this on a monthly basis. This is a log-log relationship. And there's a pretty close relationship between these two parameters, which allows us then to say the chlorophyll in the lake, where we have actual measured data, we can then associate TPP with that chlorophyll data in the lake, and it can give us a sense of if we're pulling chlorophyll out of the lake, how much phosphorus are we also pulling out. We also looked at we estimated total phosphorus in the lake using measured total phosphorus concentration, and then we converted all the concentration data that we have, meaning chlorophyll, the calculated algal phosphorus, and the measured total phosphorus concentrations. We converted all of those things into mass estimates, because when we're thinking about harvesting out of the lake, we're thinking about harvesting tons and gallons, and so we needed to have that in mass terms. Okay, so I'm going to skip right to some results because, as I said, it's a complicated set of calculations, but what we want to understand is, well, if we can harvest more algae out of the lake than current conditions in these various fetch scenarios that Randy talked about, what does that look like? So what we did is we took each one of those fetch scenarios, the low, medium, we had a third one in the middle, and then our fourth is basically the whole lake. And we thought about what if we harvested 25% of what's in those different areas, or 100% of what's in those different areas. And we could think about harvesting chlorophyll. We also wanted to put that in terms of the algal phosphorus, because again, that's what we're scooping out in the harvest. So this plot is showing us on a monthly basis, and here we're just focusing on June, July, August, and September. On the x-axis, this particular metric I'm showing you is estimated algal phosphorus, that TPP, again in metric tons, so that's our mass. And what we wanted to understand here is what are we taking out with the harvest? The gray line here is the growth of algae. So that is what the lake is producing. And if we came in and didn't harvest anything, if we just looked at existing conditions, we'll follow this black line up. We see that the bloom expands, as I mentioned before. It usually peaks, between mid-June, mid-July, and then starts to decline. So our black line goes down under our no expanded harvest condition. I will say this black line as kind of our baseline does include some amount of harvest. The current industry is harvesting a little bit. We estimated that those current operations are removing less than 2% of the algal TPP in the lake, but the black line does actually include some harvest because of its current conditions. But if we look at all of these dashed lines here, which kind of are, fairly close together, you can see they're following the shape for the most part of the current conditions. So we're shaving off some algae as we harvest 25%, 100% under these different fetch scenarios. But the only time that we really can get ahead of this curve, we can change an upward algal TPP into something that is more neutral or actually decreases early in the season in June. The only time we can really get ahead of the lake is if we're harvesting 100% of the surface area, roughly speaking, right? So that's an important finding because all these other scenarios, the areas that Randy was showing on the prior maps, don't quite get us there. It does take some phosphorus out, but it doesn't take enough out to make a big difference. Now we can also look at this in terms of total phosphorus. So same kind of figure here, but now our metric on the y-axis is TP and it goes up to a higher value. Just to give you a sense of the algal TPP is what we're harvesting, but there's other phosphorus in the lake that's not incorporated in algae, and so how does that look? And we see a very similar trend. Here the lake is, TP is coming up as the bloom comes up, and you can see that all these scenarios are very close to that black line, which is our existing condition. We do see in the 100% removal on a TP basis, we have to get into July. We're still following the general tendencies of the lake before we can really see a big difference here. So even under TP, we don't even start to see that difference in June. So again, it's very hard to get ahead of that massive biomass increase through algal harvest, even when we're looking at 100% of the lake area. So the next thing we wanted to do was say, okay, well, how do we link that to our water quality parameters to matter for fish? We did this for both DO and pH. We basically created empirical relationships between chlorophyll A and DO in the lake, and empirical relationships between chlorophyll A and pH in the lake. I'm going to show you the results for DO. This is a little bit of a complicated metric here, but what we're basically trying to do is estimate the average time for dissolved oxygen concentration in the lake to decrease to 4 milligrams per liter. And that's because we're interested in chronic water quality effects on the fish species. Getting below that really is a problem. And so at this particular location, we're using data from MDN. This is in Upper Klamath Lake. This is not the deep trench site, but it's located further in the northern portion of the lake. And the estimate is days. So on the y-axis, if we're at 0 days, that means we're basically, at 4 milligrams per liter. If we're up at, say, 30, it means it will take about a month before the waters run out of dissolved oxygen. And so we want to think about that in the same way that we looked at our phosphorus removal. The lake is producing and doing what it's doing. We're on a downward trend here as the bloom comes up in the lake. The number of days before we hit 4 milligrams per liter is going down because we're getting closer to that July-August low DO trend. And as we see our black line, here's the trend that the lake is just doing. Most of our harvest scenarios, the 25%, the 100% in the low fetch, the low and medium fetch, they're following that basic trend. They're not really making a big difference. It's this 100% removal that really starts to break away from the current trend. If we can get out and through 100% of the lake area, roughly remove the algae, then we can make a big difference in the DO signal. And that starts to happen mid-July as the bloom is actually beginning to decline. So that's where we really see the big difference in DO. We see a similar thing with pH, although I didn't include that particular slide because I wanted to also give you some cost and sort of volume estimates. So let's look at, in these various scenarios that I've been showing you, how much algae are we taking out of the lake for these particular scenarios that we're looking at. So here we have total volume of algae harvested in gallons per season. How did we come up with that? Well, in kind of our interviews and understanding with the algal harvesters, we can get a sense of gallons per hour harvested. We also learned that that is a function of wind speed, and we did several wind speed analyses to sort of, build some assumptions around that. As the wind picks up, as Randy mentioned, they can harvest less gallons per hour because the surface accumulation isn't there, and so they can't actually pull up as much. The total hours on the water that they're harvesting is also a function of wind speed. And that's because as the wind picks up, if they're being less efficient at harvesting, then they basically just pack it in and go home. So if we use that information and then look at the hours per season, we can basically come up with a gallon per season harvested for each one of our low fetch, low medium fetch, and all fetch areas in the lake. And as you would expect, we have the 25% and the 100%. So 25% is the pink and 100% is the purple. In the low fetch areas, we're basically ranging 5 million gallons to about 17 million gallons per season. And that would go up if they could actually harvest from the entire lake, but, and that would go up to probably 17 million to about 36 million, right? So that's a big difference. But they would have to harvest over the entire surface of the lake, and that actually would require technology that hasn't been invented yet, right? Because the current harvest rates that we have here is the harvest method that you just heard from Randy about. Nobody's figured out how to do this high efficiency harvest where you can go anywhere in the lake and harvest under any wind condition and still pull up meaningful amounts of algae, right? So that's a totally hypothetical high efficiency scenario. If we look at the cost then for the same kind of information, so now we're looking at dollars per season, and we can do that estimate by looking at the gallons per season harvested that you just saw. There's $1 per gallon from the harvesters. Is certainly proprietary. That's it's their business model. It's how they kind of develop and sell their products. But we have some information from discussing with them that can give us a sense of operating costs and push us towards $1 per season ballpark figure. So if we look at our low fetch current harvest rates, current technology, we're anywhere from $4 million a season on up to about $14 million a season using the current technology that's there. As we sort of move into these spaces of low and medium fetch, all fetch, you notice that our costs don't actually go up that much. And that's because we've assumed that they would have to have a higher efficiency in order to make it work. So we've built some efficiency assumptions into those costs. What they're doing right now is not particularly efficient, but it is highly selective for AFA, as Randy told us. If they're going to get out there and harvest the entire lake under all kinds of conditions, they're going to pick up everything that's out there. And that would be other algae species, green algae, other cyanobacteria potentially. And so they're going to be much more efficient. The cost may go down, but overall, we're still estimating anywhere from 8 million to something like $17 million per year. And I'll just point out that this is a harvest cost. This does not include costs of processing and then sort of marketing and selling whatever the product is. So this is just the harvest cost. All right, so conclusions, and again, this is very high level. We're happy to take questions on the details. But the current harvest methods that we understand from talking with the harvesters that are out there are really only viable in small portions of the lake. If you think back to that low fetch area, those little slivers of places where there's not a lot of wind activity, that's where they can go. The scale that's needed to improve water quality for suckers would require this hypothetical high efficiency techniques for harvest. They really have to get out in many more places in the lake and be able to harvest. Most of the lake area with our fourth scenario, they have to harvest most of the day. They can't just go out for 2 hours or 20 minutes or whenever conditions look great. They have to be out there for 8-10 hours a day. They'd have to harvest for more months, potentially pushing well into October and November, and go deeper in the water column. So they can't wait for just the scums to come up to the water surface, right? Because you need to collect much more chlorella and much more phosphorus to really reduce the water quality problems. And of course, they'd have to be much more selective. That said, the current algae market does have a lot of expansion potential, and some of the other things that we did in this project that we didn't get to talk about are, thinking about biofuels, thinking about expansion of nutraceutical and biopharmaceutical, looking at agricultural products. How can this material be used locally for ag? So you don't have to do a lot of processing, and you can just kind of put it onto crops and land areas right after it's been harvested from the lake. So there's a lot of potential there to increase harvest. But what we learned from doing these kind of short-term estimates is that most of the expanded harvest in June or later would not keep pace with the lake growth. The bottom water DO, the surface water pH would remain chronically or acutely toxic to suckers in most of our scenarios. This sort of 100% removal of algal TPP across most or all of the lake surface in July, if they could do that at a continuous rate, would actually confer some benefits of the harvest on DO improvements, pH improvements, and just improved water quality in general. And we think that that could happen starting in July based on the figures that we were looking at. It would more fully take hold in August and September as that bloom is coming down and the harvesters can pull even more out of whatever remains in the lake at that lower bloom level. And with that, if we have time for questions, we'll take questions.
Questions?
Okay, so if year one you take out 100%, how does that affect the quantity in year two?
Yeah, that's a great question. I didn't even talk about the long term. This is just short term, so thank you for asking. When we first got into the project, we were hoping to be able to model long term, but the sort of timeline of this project actually dovetailed very well with some work that Jake had been doing on sort of external phosphorus loading coming into the lake. And that work is really important because and please jump in, Jake, if I'm not characterizing this correctly, but the take home is that the phosphorus that is fueling these algae blooms is coming in largely from winter and spring runoff into the lake. There's a lot of that phosphorus is actually going right back into the algae that pops up in June. So there is an internal loading signal of phosphorus on the lake, but actually what's coming in externally is hugely important. So let's say hypothetically that they could go and harvest 100% of the algae in 1 year. That does not mean that the next year there would not be a big bloom, because it would be largely dependent on the external phosphorus loading from the watershed. That second year, you could come right back and have a lot of bloom that there would be to harvest. So I guess the good news, if you're coming at this from an algal harvester perspective, is that you're not going to harvest yourself out of a job anytime soon. But the other perspective is, if you think that harvest on an annual basis can result in a near-term improvement in water quality in the lake, that is not the case, because we have to remember that the external phosphorus loading signal is hugely important. And please jump in if I missed anything.
That was right.
This is Jake Crowley from USFWS. Out of curiosity, kind of dovetail with that question, is thinking about like constant dependence within algae. So, is there a mechanism where, harvesting actually reduces competition and increases production of algae? So you're actually taking more algae, kind of like when you cut your lawn.
Yeah, that's a
and
great
it's
question.
actually growing more because you're cutting it.
That's a great question, and we did not look into that effect of harvest. We did do a pilot study where we went out on the boat with the harvesters, and we did some water quality measurements around what's happening as they're moving the boats to the water with water quality. But it was a very short term, on the order of hours to a day, and so we wouldn't have been able to look into that kind of question at all, because there hasn't been harvest on a scale large enough to really see what the effects are. But I take your point, and it's not something that we really considered. Yeah,
I would say, light is often considered, one of the limiting factors for the bloom growth. It will literally like shade itself out. And so harvesting would, theoretically increase that light level again. And there is, a substantial amount of excess phosphorus and nutrients available. So, that likely wouldn't be a factor, at least initially. But, when we look at some of the pHs at the peak bloom point, we're talking pHs of 10 or more. And, does that create like a carbon availability, CO2 availability limitation? It's kind of theoretical. Of course, we didn't look into that specifically, but, there might be other factors that do limit the bloom growth. But yeah, it's kind of what Maia mentioned, job security, because it's not putting yourself out of business by harvesting.
Yeah, but it's a good point. There could be feedbacks that we really didn't consider at that 100%. I mean, these are really theoretical, easy to do, when you're making a map and running calculations, but in reality, the lake response could be different.
Lyra then in the back.
Chauncey just had a comment in the chat. He says you could use the USGS model from Wary and Wood 2018 to estimate the long-term responses from in-lake TP removal.
Yes, that would be great as a next step to kind of incorporate that model. We did look at the model development and we spoke with Susan Wary as part of the run up to the project, but determined that we couldn't actually run the model as part of this project. And like I said, in the long term, we ended up sort of dovetailing with the work that Jake had done to sort of think about if the external phosphorus load is the most important thing driving what's happening in the balloon, then that's sort of the answers to question from that perspective. But yes, thanks for bringing that up, Chauncey. We did have a couple of conversations with Susan as we went along on that model.
I apologize, I missed the very first part of your presentation, but I'm curious about the algae market potential if, in terms of biofuels, has that been a consideration with the inclusion of cow waste or sediment? As I understand, the particular species of algae that's being harvested doesn't have the lipid content for a good fuel, but I believe some combination of algae with some other byproduct could achieve better results.
Yeah.
And I'm also curious about, in terms of what you look at in terms of the comparison to, say, a $100,000 investment in a riparian fencing project, for example. And I think that's a very obscure question in the sense that we don't have those numbers, right? But when we talk about actually harvesting and having a direct result in measurable amount that has been removed, has that been a consideration?
Well, let me take your first question. We did, and so we just didn't have time to get into this, but maybe at a future presentation or when we finalize the report, which hopefully will be by the end of this year, we actually did quite a bit of sort of, as part of the scale up, thinking about these different end uses, and biofuels is certainly one of them. It's it's an opportunity for local use of large amounts of algae. So we did some kind of scale up calculations, see how many houses could be powered, if you could harvest all this algae. And Eli did some good work in the report, also looking at, what's the contribution that this algae source, this phosphorus source from the lake could make to overall phosphorus use for agriculture in the basin. So there's some other tidbits in there, I think, at the scale up for these other end uses that are maybe worth discussing a different time. But there's definitely potential. It doesn't seem to us, at least from what we learned, that you can harvest your way out of a near-term water quality problem with algae harvest, but it doesn't mean that there isn't potential to increase harvest and to do some useful things with the algae that's in the lake. So I don't want that to be the take home. It just, in the near term, to try to get an industry to a huge scale up and try to, solve the water quality problem doesn't seem feasible. And then your other question about, I think, like comparing the cost of doing riparian, nutrient removal in a riparian area versus trying to harvest it out of the lake. We did think about that a little bit, but not terribly much. I don't know if I'll do justice to your question, but this is obviously a very expensive venture. But I want to point out that our cost estimates are on harvest costs, right? We didn't talk about processing costs, but we also didn't talk about revenue, that whatever business is going to do this would bring in revenue and offset those costs. So our goal wasn't to kind of do a profitability analysis or anything like that. So there's more potential to look at that if various entities are interested. So thanks.
And following up, I think it's important to note that if you're doing riparian restoration or wetland restoration upstream, you're helping solve that problem at the heart of it, which is that external phosphorus loading that's out of balance. And so kind of solving it before it becomes a problem in the lake, whereas this is trying to band-aid it and address some of that excess phosphorus in the lake. So that is an important point that we need to continue focus on addressing that external load to begin with.
Chauncey has his hand up. I'm not sure if Chauncey, did you want to make a comment?
Well, just to thanks. Just to follow up to the issue about the long-term estimates. One of the results of some of that initial modeling was you don't have to take out everything to make a difference. And so Maia's charts that were showing 100% removal or 25% I don't think you need to get to 100% removal or 100% TP removal to make it worthwhile from a long-term standpoint. If you're talking about for this year and the effects on DO or pH, something like that, then maybe that is the question. But if you're thinking about a longer term, then getting to 100% probably isn't necessary.
Yeah, that's a great point, Chauncey. And also, just so folks understand, the long-term model that USGS had put together was looking at changes in external phosphorus loading and how that would affect water quality in the lake over 20, 30 years, which is why we couldn't directly use it for this project, because we were really looking at pulling out phosphorus that's already inside the lake as part of harvest. But yeah, it's point well taken, Chauncey, that, you know, you don't necessarily have, in the long term, you don't have to get it all out, but in any given year, in order to result in, you know, not going so low in dissolved oxygen and not going so high in pH, the algae really, it just grows so quickly and it's so widespread that those water quality effects are hard to get on top of, unless you're harvesting a lot. But that's a really short-term perspective versus the long-term that you're bringing up.
And if there were ever the technology advances for what is a non-existent industry in terms of this, you know, this non-selective harvest that we're talking about, you know, it would still only be kind of a piece to a puzzle of solving the phosphorus problems. You know, it's not expected to solve it all on its own. It's going to be a combination of, you know, wetland restoration, reducing erosion, upstream, you know, maybe this. So there's, you know, it's a piece to the puzzle potentially, but there's still so much that, you know, would have to happen, whether, you know, through automation or, you know, there's things that just haven't been invented yet to try to scale it up at a less labor intensive, less costly approach.
Yeah, and to be fair, we're not algal harvesters. It's a multi-million-dollar industry. Maybe somebody figured it out 6 months ago and we just don't know. There's a lot of money that's going into algal biomass reuse and, you know, in the United States in general. So I would never say it can't be done. It just, we don't know how to do that. That's somebody else's expertise.
Any last questions? Yes, no.
It seems like if we were to try to increase harvest, especially further down the water column, you could have more potential impact with suck up fish, especially like endangered suckers. Is there any kind of technology that is at this point that's like protecting those fish from getting trained in these systems, or would that have to be sort of developed as a whole nother protection?
Yeah, that's a good question. We didn't touch on permitting, but we do in the reports, we did a separate kind of technical memo on the permitting challenges around this. And so because the current industry is so narrowly focused and they're not harvesting very often, right? They're going out for short periods of time. They're very targeted. They're just at the surface of the water. They're really avoiding most of the biota interactions that you'd be concerned about from a permitting perspective. But if you were to kind of expand this to 100% of the area, you know, you've got to be out there all day long, continuous harvesting potentially. That's a very different question. And so we did look at that as part of our analyses, and it would really affect. We also looked at sort of, you know, life history stages for suckers in particular, and when they have to harvest versus what the suckers are doing at different points in their life history stage. So we could talk about that in more detail if you have questions, but it is a different permitting reality when you get to that everywhere in the lake and all the time.
And from what our conversations were with ODFW and other folks, juvenile suckers, you know, the ones we would worry about the most, during the daytime, they're not really at the surface. They're at the bottom. So it kind of avoids that problem. Doesn't mean that, like, you know, fathead minnows or, you know, zooplankton would be part of what's harvested if they're at the surface in those blooms. But that's just biomass, carbon, phosphorus in itself. So again, that less selective approach, you have to balance all that together. You know, how do you avoid capturing the suckers yet scale up? So that's an important question. All right. Well, thank you, Maya. Thank you.